Hi, welcome to Sunil Maths tutorial, Functional Analysis, class number 10. In this video, we prove a theorem. Let us see the statement. If capital N and N dash are normed linear spaces, then the set script B of N comma N dash, then the set script B of N comma N dash of all continuous linear transformations of capital N into N dash is itself a normed linear space with respect to addition and scalar multiplication of linear transformations, and the norm is defined by norm t is equals to supremum of norm t of x such that norm x is less than or equals to 1. In the previous theorem, we learned this norm as a operator norm and we prove the different forms of this operator norm. Further, if n dash is a Banach space, then script b of n comma n dash is also a Banach space. One of the lengthiest theorem, observe that. They given that n and n dash are normed linear spaces, and there is a symbol script b of n comma n dash. Script b of n comma n dash is the set of all linear transformations from capital N into n dash. Remember that. This is important point. Script b of n comma n dash is the set of all linear transformations defined from capital N into n dash. So here these all continuous linear transformations. In the statement we have all the linear transformations which are continuous is the set of all linear transform is the set of all continuous linear transformations. We add one more property. Please remember, script b of n comma n dash is the set of all continuous linear transformations from n into n dash. So further, we know that there is a standard result in the linear spaces. In the linear spaces, the set of all continuous linear transformations, forms a linear space with respect to addition and scalar multiplication of linear transformations. This is a previous, one of the important results in linear spaces. The set of all continuous linear transformations forms a linear space. They forms a linear space with respect to addition and scalar multiplication of linear transformations. So it means here you observe that script b of n comma n dash is the set of all continuous linear transformations. So from this point we conclude that therefore script b of n comma n dash is a linear space. We have to prove that. This script b of n comma n dash is normed linear space. Script b of n comma n dash is normed linear space. So first part is to show that script b of n comma n dash is a normed linear space. So further, by data the norm is given by norm t or norm t of x is equals to supremum of norm t of x such that norm x less than or equals to 1. Norm x less than or equals to 1. By using this definition of norm, we show that script b of n comma n dash is a normed linear space. So right. Here, every the norm of every element is less than or equals to 1, and norm t is defined as supremum. It is obviously norm t greater than or equals to 0, because it is the supremum of all positive numbers. Norm t greater than or equals to 0. Further, norm t is equals to 0 implies and implied by supremum of norm t of x such that norm x less than or equals to 1 is equals to 0. So which is implies and implied by norm t of x is equals to 0. Norm t of x is equals to 0. Norm t of x is equals to 0 for all x belongs to capital N, which is implies and implied by t of x is equals to 0. T of x is equals to 0, which is implies and implied by t is 0. It means which is nothing but 0 transformation. Which is nothing but 0 transformation. Therefore, from this calculation, we conclude that therefore norm t greater than or equals to 0 and norm t is equals to 0 implies and implied by t is equals to 0. This is the first property of normed linear space. This is the first property of normed linear space. Now, to prove the second property of normed linear space, let us take two elements t comma s belongs to script b of n comma n dash. Script b of n comma n dash. It means capital T maps capital N into N dash, capital S maps capital N into N dash. Both are continuous, linear transformations. Both are continuous linear transformations. Now, by definition of norm, by definition of norm, norm t plus s is equals to supremum of norm t plus s of x. I am using the definition of norm t plus s of x such that norm x less than or equals to 1. This is equals to supremum of norm t of x plus s of x such that norm x less than or equals to 1. Norm x less than or equals to 1. Split the norm. Split the norm, which is less than or equals to supremum of norm t of x plus norm s of x such that norm x less than or equals to 1. Again split the set. Split this set. Supremum of norm t of x such that norm x less than or equals to 1, norm x less than or equals to 1 plus supremum of norm s of x such that norm x less than or equals to 1. Here this first set is nothing but norm t of x, and the second set is nothing but norm s of x. This is the second property of normed linear space. This is the second property of normed linear space. Therefore, in the LHS we have norm t plus s. In the right side we have norm t plus norm s. Therefore, norm t plus s less than or equals to norm t plus norm s. This is second property of normed linear space. To prove the third property, let us take a scalar. Alpha belongs to capital R, be a scalar, and t is a element from script b of n comma n dash. Now norm alpha t is equals to, I am applying the definition of supremum. Norm alpha t is equals to supremum of norm alpha t of x, norm alpha t of x, such that norm x less than or equals to 1. It is very simple and very easy. Supremum of mod alpha norm t of x such that norm x less than or equals to 1, which is equals to mod alpha into supremum of norm t of x such that norm x less than or equals to 1. This is nothing but mod alpha into norm t. This is nothing but third property. Norm alpha t is equals to mod alpha into norm t. This is nothing but third property of the normed linear space. Now let us see. This is the first condition. Norm t greater than or equals to 0, and norm t is equals to 0 implies and implied by t is equals to 0. First property of linear space. Norm t plus s less than or equals to norm t plus norm s, which is second property of normed linear space. Norm alpha t is equals to mod alpha into norm t, which is the third property of normed linear space. From all these three properties, we conclude that script b of n comma n dash is a normed linear space. Is a normed linear space. Further, the second part of the theorem. Next, the second part of the theorem. Assume that n dash is a Banach space. Assume that n dash is a Banach space. Assume that n dash is a Banach space. We have to prove that. By using this fact, we have to prove that script b of n comma n dash is also a Banach space. Is also a Banach space. Already script b of n comma n dash is a normed linear space. So it is equivalent to show that it is sufficient or equivalent to show that script b of n comma n dash is Banach space. We prove that it is complete. It is complete. It means already it is a normed linear space. If we show that it is complete, then obviously it becomes a complete normed linear space becomes a Banach space. I repeat this point, please understand. We have to prove that b of n comma n dash is a Banach space. Already we prove that it is a normed linear space. Already we prove that it is a normed linear space. So it is equivalent to prove that it is a Banach space means you have to prove that it is a complete. A complete normed linear space is again a Banach space. So right, to prove this it is a Banach space. To prove this it is a Banach space. Define a Cauchy sequence. Let us take sequence Tn be a Cauchy sequence. Sequence Tn be a Cauchy sequence in script b of n comma n dash. By the definition of Cauchy sequence, for each epsilon greater than 0, there exists a positive integer n naught. There exists a positive integer n naught such that norm Tm minus Tn less than epsilon for all n comma m greater than or equals to n naught. For all n comma m greater than or equals to n naught. This is from the definition of Cauchy sequence. We take a Cauchy sequence. Tn is a Cauchy sequence in script b of n comma n dash. By the definition of Cauchy sequence, for each epsilon greater than 0, there exists a positive integer n naught such that it satisfies the condition norm Tm minus Tn less than epsilon for all n comma m greater than or equals to n naught. This is from definition of Cauchy sequence. Now let it be equation number 1 or equation number 4. Already we used 3 numbers, so let it be equation number 4. So right. Now define an arbitrary element. Let us take x be an arbitrary vector, small x be an arbitrary vector in capital N. If it is an arbitrary vector in capital N, then Tn of x obviously belongs to n dash. Tn of x belongs to n dash means the sequence Tn of x is also belongs to capital N dash, because Tn is a linear transformation from n into n dash. All the images of Tn of x, they are compulsory belongs to n dash. So Tn of x belongs to n dash. It means Tn of x is a Cauchy sequence. Tn of x is a Cauchy sequence in capital N dash. In capital N dash. In the second part, we assume that N dash is a Banach space. N dash is a Banach space. In the second part, we assume that N dash is a Banach space. What is mean by Banach space? Banach space means it is a complete normed linear space. It means Tn of x is a Cauchy sequence. Tn of x is a Cauchy sequence in n dash, and this n dash is complete. What is the definition of complete? Every Cauchy sequence in it is convergent. Every Cauchy sequence in it is convergent. It means norm Tm of x minus Tn of x is less than or equals to norm Tm minus Tn of x. So which is again, I think it is equivalent to, and then we go for in the next step we are going to equivalent. We write which is equals to, which is less than or equals to. We are splitting the norm. Please see carefully. Now it is less than or equals to norm Tm minus Tn into norm x. We use this condition, this less than or equals to property, because of in the previous class we learned that whenever t is continuous linear transformation, they satisfies one condition. Norm t of x is less than or equals to norm t into norm x. We learned the same property in class number 9. Please remember that. So here by definition of our norm x less than or equals to 1. So applies that norm Tm minus Tn. That's it. And equation 4. Let us see equation 4. What is equation 4? Norm Tm minus Tn is less than epsilon. By applying this equation number 4, it is clearly less than epsilon. Therefore, norm Tm of x minus Tn of x is less than epsilon. Equation number 5. So remember this point. From equation number 4 and 5. From equation number 4 and 5. M comma n greater than or equals to n naught, and norm Tm of x minus Tn of x is less than epsilon, which implies as norm Tn of x is a Cauchy sequence in capital N dash. Again, since capital N dash is complete because it is a normed linear space, we have this sequence Tn of x is convergent. And say it is converges to T of x. What it means? Tn of x tends to t of x as n tends to infinity. That is, limit n tends to infinity, Tn of x is equals to t of x. Here, let us see 1 minute. Here you observe that equation number 5 and you observe that equation number 4. There is small difference between these two, equation 4 and equation 5. In equation 4 and equation 4, we are representing Tn or Tm. They are only linear transformations. They are linear transformations. And in equation number 5, it is Tm of x and Tn of x. You observe that there is a small difference between 4 and 5. In the 4 we write only Tm minus Tn. In the 5 we write Tm of x minus Tn of x. The second condition, this condition is true for all x belongs to capital N. Here we don't say that for all x, here just for a linear transformation only. But here for every linear transformation as well as for all x belongs to capital N. That is the difference between equation 4 and equation 5. Please remember that. Now we have a Cauchy sequence which is converges to t of x. We have to prove that now we shall prove that capital T is continuous linear transformation. Capital T is continuous linear transformation. So we start with very basic. First we show that it is a linear transformation. So x comma y belongs to capital N, alpha comma beta belongs to the field capital F. Obviously, this alpha x plus beta y belongs to capital N because N is a linear space. N is a linear space. So alpha x plus beta y belongs to capital N. Now we consider T of alpha x plus beta y, which is equals to limit n tends to infinity, Tn of alpha x plus beta y, We prove the same thing in this step. Limit n tends to infinity, Tn of x is equals to t of x. So T of alpha x plus beta y is equals to limit n tends to infinity, Tn of alpha x plus beta y. It can be written as limit n tends to infinity, Tn of alpha x plus limit n tends to infinity, Tn of beta x. This can be written as alpha into limit n tends to infinity Tn of x plus beta into limit n tends to infinity, not plus, into beta into limit n tends to infinity Tn of beta x. You simply write alpha into t of x plus beta into t of x. Therefore, we conclude that t of alpha x plus beta y is equals to alpha into t of x plus beta into t of y. I am sorry, this is y. Therefore, here also every time I write x instead of x, that is y. Please remember that, correction this point. This is not x, this is y everywhere. Beta y, here also y, it is here also y, here also y. So capital T is a linear transformation. Now we show that T is continuous. By definition, T of x is equals to limit n tends to infinity Tn of x. Norm T of x is equals to norm limit Tn of x, which is equals to limit norm Tn of x. This is simple mathematical calculation which is less than or equals to supremum of norm Tn of x, which is less than or equals to supremum of norm Tn into norm x, which is less than or equals to, supremum of norm Tn, we treat it as k, and norm x less than or equals to 1. So here you observe that take supremum of norm Tn is equals to k And already we have norm x less than or equals to 1. Using these 2 points here, you get this is less than or equals to k. It means norm t of x is less than or equals to k for all x belongs to capital N. This condition implies as capital T is bounded. Capital T is bounded. By previous theorem, a bounded linear transformation is always continuous. Therefore, capital T is continuous linear transformation. Capital T is continuous linear transformation. If capital T is continuous linear transformation, capital T belongs to script b of n comma n dash. Script b of n comma n dash. So we prove that there is a Cauchy sequence Tn. There is a Cauchy sequence Tn of x that converges to T of x, and the T of x is a continuous linear transformation which belongs to script b of n comma n dash. And finally, we show that the sequence Tn converges to T. The sequence Tn converges to T. From equation number 5, already we have norm Tm of x minus Tn of x is less than epsilon for all n comma m greater than or equals to a positive integer n naught. Now hold small m is fixed. Hold small m is fixed and allow n to approach infinity. Remember that we are allowing small m is fixed and we are holding m is fixed. We are allowing small n to approach infinity. Then obviously we have norm Tn of x minus Tn of x tends to norm Tm of x minus T of x. Thus we conclude that norm Tm of x minus T of x is less than epsilon. This is nothing but norm Tm minus T is less than epsilon. Remember this in mind. Now consider, we give one more, we consider norm Tn of x minus T of x is equals to norm Tn of x minus Tm of x plus Tm of x. I am subtracting and adding the same terms, plus Tm of x. You can write now minus T of x. So split them out, less than or equals to norm Tm of x minus Tn of x plus norm Tm of x minus T of x, which is less than or equals to norm Tm minus Tn into norm x plus norm Tm minus T into norm x, which is less than or equals to epsilon plus epsilon 2 epsilon. Or if you define this epsilon by 2, which is equals to 2 epsilon, and a very small number, epsilon is a very small real number. This shows us norm Tn of x minus T of x is less than a positive real number 2 epsilon. So this condition implies as norm Tn minus T is less than epsilon for all x belongs to capital N, or 2 epsilon for all x belongs to capital N. Thus the sequence Tn converges to capital T in script b of n comma n dash. So the sequence Tn, every Cauchy sequence Cauchy sequence script Tn converges to T in script B of n comma n dash. Therefore, script B of n comma n dash complete is complete. Already it is a normed linear space. Now we prove that it is a complete normed linear space. Therefore, script B of n comma n dash is a Banach space. Is a Banach space. Remember that this is a Banach space whenever n dash is a Banach space. This completes the proof of the theorem, and one of the very lengthiest theorem, and I explained in detail also. So go through with the proof carefully. So that's it. Keep learning. In the next video, we learn one more theorem depends upon the functional analysis. Please go through with it. Keep learning.